on? Well, f prime is equal to 0 at these 2 points that are marked. And so when f prime is equal to 0, what does that tell us about the original function f?
Flat.
It's flat. Okay, so the original function f is flat. Now here at this first point, and maybe I'll call that a, so f prime is changing from positive to negative at x equals a. So when f prime is going positive to negative, that means my original function is going from uphill to downhill. So here we've got something that looks like this. It's going to be flat right at x equals a, and then moves downhill.
Yeah,
Now at b, at x equals b, f prime is going from negative to positive. So that means that the original function f is going from decreasing to increasing. And so I know that my original function f will be decreasing, get flat right at x equals b, and then increase. And so my picture of f is going to look something like this. Now, again, does your graph have to go through 0, 0? Absolutely not. Your picture could be higher. It could be lower. Okay. It might be a little squished flat. That all depends on what you imagine your scale to be. Okay. But the general shape of uphill, downhill, uphill should be what your picture looks like for f. So, note. All graphs of f should have the same shape, but will differ by a vertical shift. Okay. Are there any questions about that? About that picture? Some other details which you might think about in terms of review, notice that we have a local minimum on f prime. That corresponds to the inflection point on our original function f. Okay. So that's a bonus piece of information. Local minimum on f prime corresponds to inflection point on f. And yeah, that's about it in terms of our information. Okay, so here's another example for you. This time, what we're given is f prime of x is equal to a formula. F prime of x is equal to 2x. So the question is, what was the original function? So think about it for a second and write down your thoughts. All right, so now that you've thought about it for a minute, tell your neighbor what you think.
2x.
All right. Anybody have a thought? X squared? Okay. Anybody come up with something different than x squared? Yeah, okay. I mean, I could write down x squared, or f of x could be equal to x squared plus 72, because when I take the derivative of a constant, that derivative is equal to 0. Or I could have f of x is equal to x squared minus 375.23. When I take that derivative, I also get 2x. And so it turns out that x squared is a valid original function whose derivative is 2x. But in general, if we want to list all of the possibilities whose derivative is 2x, then what we want to write down is that f of x is equal to x squared plus some unknown constant. All right. So what this describes, when I write down that f of x is equal to x squared plus some unknown constant, this describes a whole family of functions whose derivative is 2x.
So it's not possible to get the exact original function.
That's right. So unlike when we start with a function and take its derivative, we have one answer for our derivative. But if we start with a derivative and want to find the original function, we actually cannot retrieve all of the original information because we have no idea if there was some constant added on there. Once we take the derivative, we lose that constant. So in fact, when we work backwards, we cannot get one single function, we get a whole family of functions, and those functions differ by a constant or differ by a vertical shift.
So then how do you use that information? Like, is it useful?
It is. Hold that thought, and we'll see an example. So right now, we don't have that extra information, but what we'll do is we'll have a bonus piece of information, and that will allow us to figure out what that constant should be for the particular example that we're looking at. Okay. Other questions about this?
So the original function can't be like 1.5x to the 1.3 or something, so that you can.
So you might be able to come up with a different format, a different way of looking at x squared, but it will still be the same shape graph. You're not going to get a graph that has a different shape. The only way that the graph can differ is by a vertical shift.
So in this case, we're just going back from a derivative to its original number.
That's correct.
We don't know if it is a derivative at the first place.
So what happens if I then say, well, if I imagine that this is a derivative, then what was the function that came before it? Well, that's a good question. Do we know if did it come from, is that truly a derivative? And the answer to that is that there's a lot of work that goes into answering your question. And that's about at least a third of Calc 2. Okay. So good question, I'm not going to answer it today. Okay, so let's look at another example. Okay, so on this example, we have f prime of x is equal to 8x cubed plus 12x plus 3. All right, so I'd like you to think about how you would work backwards to get the original function f of x. And when you write down your idea, you can always check by taking the derivative of whatever you write down to make sure you get f prime.
sure you already got an answer, so I'm just gonna add C to it.
Huh?
I said, I'm sure you probably already got an answer, so I'm just gonna say,
You're gonna
add
second
attach
it?
a plus C to it.
All right.
I don't know, do you have the plus C already? Yeah, well, I put a
Oh,
plus C.
yeah, you're right, yeah. Good. Good plan.
Good, yeah.
Okay, so we have a least quantity that looks like 2x to the fourth plus 6x squared plus 3x plus c. And so kind of thinking about what's happening here, this makes sense because when we take a derivative, we subtract 1 from the power. And so here we're going to add 1 to the power. And so if I double check and take the derivative of 2x to the fourth plus 6x squared plus 3x plus whatever numbers at the end, well, 2x to the fourth, the derivative is 8x cubed, 6x squared, derivative is 12x, 3x, its derivative is 3, and then it's a bonus we want to throw on this plus c because when we have our derivative, we have no idea if the original function had a constant on the end or not. Okay, so in the process of thinking about this, I haven't given you any sort of any sort of recipe for coming up with the original function based on being given the derivative. Right now I'm just asking you to think about, okay, if you were to work it backwards in your head, would you come up with this? Okay, so this right here is our original function. Are there any questions about that original function? Okay, so this plus c on the end, the thing about that is, again, if I were to graph f of x on my calculator and do plus 1 or plus 20 or plus negative 375, the shape of the graph would be exactly the same. The only difference is a vertical shift upwards or a vertical shift downwards. Okay. So that plus c gives us this whole family of functions, all of whose derivative is 8x cubed plus 12x plus 3. Okay, so then we'll ask the question of, well, is there any way to come up with that value for c? And the answer is, well, no, not with the information we have here. However, if we know just one point on the original function, if we know one piece of information, if we know, for example, that f of 1 is equal to 6, if we know one little piece of information about the original function, from that piece of information, that is going to take our shape and it's going to thumbtack it on to the right height. Okay? And so if we know f of 1 is equal to 6, then we can figure out what the c value is that will work to make f of 1 equal to 6. So how do we do that? Well, if I know that f of 1 is equal to 6, then I can write down that f of 1 is equal to 2 times 1 to the fourth plus 6 times 1 squared plus 3 times 1 plus c. And I know that f of 1 is equal to 6, so all of this had better be equal to 6. Okay. And the 1 and the 6 I made up just specifically for this example, so those are numbers that I pulled out of my head. Okay. All right. So if we know that f of 1 equals 6, then I can solve for c. We've got 2 plus 6 plus 3 plus c equals 6. And so we've got 11 plus c is 6, so c must be equal to negative 5. So what that tells us is the correct formula for f when we know that f of 1 equals 6 is f of x is equal to 2x to the fourth plus 6x squared plus 3x minus 5. So if we know two pieces of information, if we know what the derivative is, and we know just one point on our function, 1 comma 6 in this case, then we can figure out what the original f was specifically. Okay, any questions about that? Okay, so some notation. The antiderivative of f prime of x is f of x. Now, if I go backwards one more, then the antiderivative of f of x is, and here's the new notation, the antiderivative of f of x is capital F of x. Okay, so let's talk about some rules. Some antiderivative rules. If f of x is equal to x to the n, then capital F of x is going to be equal to something. Okay? So let's think about this. When we take a derivative, the first thing that we do is that we bring that number, well, let's see, what is the very first thing we do? The first thing we do is we bring the original power down in front, and then we subtract 1 from the power. So, to find y prime, when y is equal to x to the, let's just say x to the 5th, step 1 is to multiply by 5, and step 2 is to subtract 1 from the power. So that's how we would normally take a derivative. Our power rule derivative of x to the 5th becomes 5x to the 4th. How did we do that? We brought the old power down, and then we subtracted 1 from the power. So an antiderivative is going to undo this process. Now, if we work down this way to make the derivative, then to undo the derivative, we've got to work back up in the opposite way. So if we subtracted 1 from the power, we're now going to add 1 to the power. And if we multiplied by that power that's written up there, we are now going to divide by that power. And so our derivative looks, or I'm sorry, our antiderivative looks like 1 over n plus 1 times x raised to the n plus 1. So, for example, if I have f of x is equal to x to the 7th, then my antiderivative says to add 1 to the power and then divide by the new power, or multiply by the reciprocal. And since I don't know if there was a constant on the original function, I need to tack on a plus c. And so up here in my derivative rule, I also have a plus c on there. And you can double check. The nice thing about doing antiderivatives is that you can check your work by taking a derivative, and the derivative of 1/8 x to the 8th is x to the 7th. Okay, any questions about that? Okay. So a few other antiderivative rules that we might think about. I might think about if f prime of x is equal to sine of x, then the original function f of x, yeah, it would have been negative cosine x, because when you take the derivative of cosine, the derivative is negative sine, so to cancel that negative, you've got to toss in an extra negative in the beginning.
Plus C.
And we need a plus c. Great. Okay, so some others that go along with this, so thinking along those lines, so if f of x equals sine x, then the antiderivative, capital F of x, is equal to negative cosine x plus c. We can do some similar ones if f of x is equal to cosine x, then the antiderivative, in other words, what function gives us the derivative as cosine?
Negative sine x plus c.
Negative sign.
So it will be negative or positive sine?
Positive.
Should be positive, because when I take the derivative of sine x, my derivative is positive cosine. So sine x plus c. All right, there's a few other silly ones that we can look at, such as if f of x is equal to secant squared x, then what was the original function, the antiderivative? Yeah, derivative of tangent is secant squared, so the antiderivative of secant squared x is tangent x plus c. So we're working backwards on all of these. There's lots of other trig ones. I'll let you think about those on your own. But in addition to the trig ones, we also have exponential functions. So if the original function f of x is equal to e to the x, then the antiderivative, capital F of x, is that gonna be? Yeah, that's going to be e to the x, because the derivative of e to the x is just e to the x.
Yeah.
And then we need plus c. If f of x is equal to 1 over x, and let's talk about this one for a second. 1 over x is the same as writing x to the negative 1. Okay? So if I think back to this power rule over here that I have written down, if I have x to the negative 1, and I apply this power rule over here, if f of x is equal to x to the negative 1, then my antiderivative, according to my power rule over here, says, okay, we're going to add 1 to the power. So we'd have x to the 0, and we are going to divide by that new power. And so we run into a problem here. When n is equal to negative 1, this rule will not apply. Okay? So initially when I wrote that rule down, I lied to you a little bit, because I said that this rule would work as a power rule, but this rule only works as long as n is not equal to negative 1. But luckily, we can look at 1 over x. 1 over x is the derivative of what function? Natural log. So the antiderivative of 1 over x must be the natural log function. Plus c. Now, there's a small detail, and this is a mathematical technicality, and this is that when I look at 1 over x, the only restriction I have on 1 over x in terms of domain is that x cannot be equal to 0. Whereas natural log, the domain for natural log is only positive numbers. And so if I started out with 1 over x and took the antiderivative and got natural log of x, I'd have issues when x was negative. And so the way that I deal with that is that I throw in absolute values in my antiderivative.
What happens if you have f of x is ln of x? How do you go back from that?
That's a really good question. And so if f of x is equal to the natural log of x, then the antiderivative is equal to, wait for calc 2.
All right, well, at least that won't be on the test.
All right. Okay. So here are some antiderivatives. Are there any questions about those? Okay. So I will wrap up this portion with an example of a velocity question. So a particle's velocity is given by v of t is equal to 2e to the t plus 3 times the sine of t. The particle's position at time t equals 0 is given by s of 0 is equal to 0. So the particle's position at time 0 is a position of 0. Find s of t, the position of the particle. So we are trying to find a formula for the position of the particle. Now, we are given the velocity, which means we need to go backwards and come up with the original position function. So we're starting with v of t, which, by the way, is s prime. And we're told that that is 2e to the t plus 3 times the sine of t. So when we go backwards, yeah, so if you don't like t's, put make them x's, that's fine. So we have 2e to the t plus 3 times the sine of t. When I take the antiderivative, in terms of coefficients in the front, I can carry them along just like I did with derivatives. So my antiderivative of e to the t is still just plain e to the t. So this antiderivative looks like 2e to the t. My antiderivative of sine is negative cosine, so I have minus 3 cosine of t. And there was some sort of a constant, but I don't know what it was, so I write down plus. So this is my position function, but with this mystery c on the end. So now I'm going to use my extra piece of information. We know that s of 0 is equal to 0. Well,
So how come that 2e to the t couldn't be e to the 2t?
e to the 2t. So if I take the derivative,
Oh, never mind. Yeah, I see.
yeah, if I take the derivative of this, I'd have
Okay.
2e to the 2t.
Gotcha.
Okay, so we know s of 0 equals 0. So I can plug in 0 for t. So we have 2e to the 0 minus 3 times the cosine of 0 plus c. Now the zeros that I plugged in here in for t, those are the zeros that came from s of 0. And then we're going to set this whole thing equal to 0. That came from because the position was 0. Okay, so now we can do some number crunching. 2e to the 0 is 2. Cosine of 0 is 1, so we have 2 minus 3 times 1 plus c equals 0. And so we've got c is equal to a positive 1. So in the end, once I put this equation together with my original function, then my final answer is that s of t is equal to 2e to the t minus 3 cosine of t plus 1. And this describes the position of my particle exactly. All right, any questions about that? All right, so we've just talked about antiderivatives, and what I want to encourage you to do is to write down these practice problems, but maybe